materials as the first topic of today's presentation. In between, I'll be pausing and you can just raise the question if you have any doubts. Okay, so fiber optic materials. This topic is related to what are the raw materials that can be used in order to fabricate the optical fibers. So the basic materials which we will be using, or the basic materials which are required for fabrication of optical fibers, are glass and also plastics. So fiber optic cables can be fabricated either using glass, that is silicon dioxide, or composition of plastic material. So we have two classifications. One is glass fibers and other one is the plastic fibers. First I'm be introducing what is glass fiber. Glass fiber is basically constructed or fabricated using the silicon dioxide as a raw material. So glass is made up of a fusing mixture of metal oxides, sulfides, or selenites. So that is how glass material is being manufactured. Making use of silicon dioxide, which is abundantly available. So we are going to use that as a raw material in order to fabricate glass fibers. So a pure silicon dioxide is of no use, so we need to add some dopants to that in order to change the refractive index. So these are some of the dopants which is mentioned here: B2O3 boron trioxide, GeO2 germanium dioxide, P2O5 phosphorus pentoxide. These are the dopants that can be added to silicon dioxide in order to change the refractive index profile of the optical fiber that is made up of glass. You can just go through this plot which shows the refractive index profile on the y-axis and the dopant addition on the x-axis. So based on the amount of dopants that you are going to add will change the refractive index. Say for example, if you are adding boron, say 20 dopants for it may result in, say, refractive index of 1.44, or if you are using germanium dioxide, it can reach up to 1.48, the refractive index. I'll pause here. If you have any doubts, you can just raise the questions for 2 minutes. Hello. Hello.
Yes.
Yes. Any questions? Many of you have muted your audio also. You can just turn on your audio so that you can have the conversation. Yes, Pawan Reddy. Pawan Reddy, can you hear?
Okay.
Pawan Reddy.
Yes, sir.
Are you able to follow the conversation?
Yes, sir. I'm reading the slides.
Okay. Any doubts you have? Okay, right then. I'll be continuing with the presentation now. Addition of dopants will increase or decrease the refractive index profile. So you can see here we have a compositions like GeO2, SiO2, which are used to fabricate your core part of your optical fiber, and only SiO2 will act as a cladding in that case. If you want to increase the refractive index, you need to add dopants such as GeO2 or P2O5, germanium dioxide or phosphorus pentoxide. If you want to reduce the refractive index, you need to add the trivalent impurities like boron and fluorine. So these are the raw materials which are used to fabricate our glass fiber. So coming to the next type of optical fiber raw material which is used, it is plastic. So plastic can also be used as a raw material. In this case, we'll be using the composition of different polymers which are used in order to fabricate the optical fibers. And the advantage of going for plastic optical fibers are they are not brittle as glass fibers, and they are lighter in weight, and plastic fibers are 10 to 20 times larger, which allows the relaxation of the connector tolerances without sacrificing the optical coupling efficiency. So these are some of the advantages in which the plastic optical fibers will offer over the glass fibers. But the coming to the transparency property, plastics are not that transparent compared to glass fibers. So most of the industrial optical fibers are based on glass material than plastic optical fibers. So with that, I'll conclude with the fiber optic materials which are used in fabrication of optical fiber. So I'll be moving with the next topic, that is photonic crystal fibers. So till now, whatever optical fibers that we have seen, they had only two concentric layers, that is core and cladding, with different refractive index profiles. And photonic crystal fiber is a type of an optical fiber which is not a conventional one, but it is a specialty fiber. So why it is specialty fiber? Because you can have a different construction inside the optical fiber. Say for example, an array of hair holes can be uh, placed inside an optical fiber, uh, or you can have a different refractive index inside the core. So those are the compositions or the configurations that you can have inside the specialty fiber, which we call it as photonic crystal fibers. So in PCF, in short form, we call it as PCF. We have two categories. One is the index guided microstructures. In index guided microstructures, the core will have the higher refractive index, and the cladding is completely filled with air holes, uniformly arranged air holes. So in the next slide, I'll be showing the diagrams. This is the first type of photonic crystal fiber, index guided microstructure. The second is photonic band gap fibers, in which the core will have the low refractive index, and cladding will have the higher refractive index, and the core is filled with air holes. Or we also have other combination where core is filled with the solid silica of so this is the structure of index guided microstructure, which is a specialty fiber. You can see we have a solid core with a high refractive index, and the cladding is made up of uniformly arranged circular or hexagonal shape of hair holes. And we have a parameter called as pitch. Pitch is nothing but the separation between the two hair holes, adjacent hair holes, that will define the wavelength or the property in which the optical fiber is going to operate. Two parameters, one is the pitch and the hole diameter. Pitch and the hole diameter will decide in what wavelength and what is the bandwidth in which the optical fiber is going to operate. This is index guided microstructure where core is having the high refractive index, and the cladding is made up of uniformly arranged circular or hexagonal shape hair holes. You can see here the hole has a diameter d and a pitch vertical v, and hole to hole spacing. Pitch is called as hole to hole spacing, which are critical design parameters which used in specifying the structure of photonic crystal fiber. So another structure of specialty fiber, that is photonic crystal fiber, you can see index guided PCF, in which the core is a hair hole and the cladding is made up of a solid cylinder. The cladding is made up of hair holes and core is solid silica. Another structure of index guided PCF. So coming to band gap fibers, photonic band gap fibers, which is opposite to that of whatever the first diagram of index guided microstructure that we had seen. Here in this band gap fiber, photonic band gap fiber, we have a hair hole which is acting like a core, but it was the solid silica in that index guided microstructure. So here it is a hair hole which is a hollow core, and the cladding is made up of embedded hair holes. So this is a structure which is opposite to that of what we saw in the index guided microstructures. The difference between index guided photonic crystal fiber and band gap fiber is index guided photonic crystal fibers are used for all possible wavelengths, whereas photonic band gap fiber, that is this structure, which is used only for certain wavelength band or a certain frequency of operation.
Sir, where is it exactly used?
Which one?
This one only, sir. This photonic
The specialty
fibers.
fibers. Okay. Specialty
Yes,
fibers are not for long distance communication. They are used, say for example, if you need to have what you call different wavelengths at different uh, time instant that you have to transmit in, say, multiplexing, demultiplexing the signals, multiple signals.
Okay, sir. Yes, sir. Yes.
In those applications, these specialty fibers are used, but the conventional fibers are the one which will be carrying your information for long distances in terms of kilometers. These photonic crystal fibers are only for handling the multiple wavelengths and at different time instances.
Fine, sir. Understood, sir.
Okay. So that's about photonic crystal fibers. So I'll move on to fiber optic cables. This is a small topic with which we'll wind up the first module. This is structure of how the cable looks like, optical fiber cable. Hello. Yeah. So structure of optical fiber cable. If any of you have gone through the optical fiber, you can just see it. We have different structure of optical cables. Don't get confused with the fiber optic materials and cables. Materials are nothing but the raw materials which are used in fabrication of fibers, but fiber optic cables are nothing but your physical cables which are going to carry the fibers. Cables are nothing but a combination of optical fibers, which we call it as cables.
Optical fibers.
So the first structure which is displayed here on the screen is, it's a 2-fiber cable design. You can see a single cable on the left hand side and the same basic building block on the right hand side. So each single cable is it is not just a fiber which is being carried inside the cable. Multiple coatings are done in order to protect the optical fiber. So these are some of the coatings or package that is being done for an optical fiber. So you can see in the middle we have a glass fiber which is being covered by multiple layers, and it varies as the requirement is going to change. So you can see polyurethane buffer material, a polyethylene tube, and then strength member. These are some of the packing materials in order to protect the glass fiber, and the number of layers will vary from fiber to fiber. So this is an hypothetical 2-fiber cable design. On the second diagram, you can see a 6-fiber cable where 6 optical fibers are being carried inside a single cable, and you can also see the different layers in which these 6 fibers are being protected. First one is a 2-fiber cable design. The second one is a 6-fiber cable design. And third one is a ribbon type, where in which the 12 ribbon cable, all the each circular shape is a single fiber along with the package. So you can see 12 fiber ribbon cable module. This is the third diagram. So devices which are using specialty fibers, I think I've answered the question which has been asked. So you can just go through the screen. Devices used in using the specialty fibers are light transmitters, receivers, wavelength multiplexers, demultiplexers, couplers, splitters, optical add-drop multiplexers. So these are some of the devices which make use of specialty fibers, as we discussed earlier, that is PCF, photonic crystal fiber, index guided, as well as band gap fibers. So what are the applications of specialty fibers? So example application what it is mentioned here are specialty fibers are used in construction of optic fiber amplifiers. Optic fiber amplifiers are nothing but it's an optical device which is purely made up of optical material, which is totally different from your electrical amplifier. And PCFs are also used in optical switches, dispersion compensators, and some of the other examples like couplers, wavelength division multiplexers, and also fiber gratings. Fiber gratings will be discussed in module 4. So these are some of the applications in which the photonic crystal fibers are being used. But these are the major applications, but photonic crystal fibers are still used in some of the other applications. And please remember, PCFs are not used for the carrying of signal from one distance to other distance. They are used in some certain devices like transmitters, receivers, and multiplexers. So with this, we came to an end of module 1. Today, we had discussed about fiber optic materials, specialty fibers, in specialty fibers, that is photonic crystal fibers and band gap fibers. And we also see the structures of PCF, that is photonic index guided microstructures, and band gap fibers. And along with that, we also saw some of the structures of optic fiber cables, like 2-fiber cable design, 6-fiber cable design, and 12-fiber ribbon type design modules. So I'll just pause for 2 minutes. If you have any questions, you can raise. Hello. So we'll move on to the second module. If you have any doubts, you can just ask for a minute regarding first module, so that I can start with module 2, that is transmission characteristics of optical fibers. So transmission characteristics of optical fibers. Here in this module, we are going to understand what are the different characteristics that the optical fibers are going to operate for the transmission of our information. So this entire module is been classified into two things. One is attenuation. The second one is bandwidth. So what is attenuation? Attenuation is nothing but it's a transmission loss that is being offered by optical fiber as the signal propagates throughout the length of the fiber. So we have different types of attenuation, which will be discussed in detail in this module. The first attenuation we just go through is material absorption. What is material absorption? So because optical fiber is made up of different materials, as we saw in the previous section, like glass or plastic, and different composition of different materials like silicon, germanium, trivalent impurities, and pentavalent impurities, which are used in variation of refractive index. These materials themselves will absorb certain information which is being transmitted inside the optical fibers, and they result in material absorption. Second is linear scattering losses. Scattering is nothing but the deviation of light away from the optical fiber core as the signal propagates throughout the optical fiber. And in linear, in scattering, we have two categories. One is linear and non-linear scattering process. We're going to discuss in detail of what is linear and non-linear scattering in the coming discussion. And third type of attenuation is bending. So fiber bending loss. So we have two classifications in fiber bending loss. One is micro bending, the other one is macro bending. Macro bending is nothing but physically bending the optical fiber beyond certain radius of curvature. And micro bending is during the manufacturing process. If a core or the cladding structure is being micro bent, that itself results in deviation or um, attenuation of signal throughout the length of the fiber. So that's about fiber bending loss. So overall attenuation is because of material absorption, scattering, and bending loss. All these three will contribute to overall attenuation of optical fibers. And as I was mentioning, this is the first part of the module 2, that is about attenuation. And the second part of the module 2 discusses about the bandwidth. The bandwidth is directly related to our dispersion. Dispersion is nothing but the spreading of light as the light propagates inside the fiber. Say for example, if you take a digital pulse, if you are allowing a digital pulse to be transmitted in an optical fiber, as it propagates throughout the length of the fiber, after certain length of kilometers, the pulse will get broadened, and the broadening of the pulses will result in dispersion, that is nothing but spreading of light. As the dispersion increases, the bandwidth that is being offered by the optic fiber cable will uh, reduce. And as the pulse gets broadened, and if you are transmitting multiple pulses, the pulse will get overlapped on the other pulse, that results in symbol interference also, which uh, contributes to reduction in the bandwidth. So one has to take care of how the dispersion can be compensated using passive and active approaches that will be taken care of in module 4. There are some of the passive and active devices which will take care of the dispersion compensation. So coming back to the introduction of this transmission characteristics of optical fibers. So attenuation or loss is usually expressed in terms of decibels. So loss in dB is equal to 10 log to the base 10 of pi by p naught, that is input power divided by output power, or it is also expressed as minus 10 log to the base 10 of p naught divided by pi. P naught is the output optical power and pi is the input optical power. So dB is nothing but 20 log to the base 10 of V naught by Vi in electronics, but here in optics, we are going to use dB as 10 log to the base 10 of input power divided by output power. That is nothing but the ratio of input power to the output power in logarithmic scale will give us the loss or attenuation in terms of decibels. So if you want to get a numerical value, if not in terms of decibels, you can just take the antilog of that, which will give you the ratio of output to input power. So attenuation in optical fiber is usually represented using a standard unit called as dB per kilometer. So we are interested in measuring the attenuation for every kilometer length of the optical fiber rather than for the entire length of the optical fiber. So in that case, alpha is nothing but the overall attenuation into L will give you the length of the optical fiber for every kilometer. So in that case, it is minus 10 log to the base 10 of P naught by Pi, where alpha is in dB per kilometer, signal attenuation per kilometer, and L is the fiber length. So this expression is important because we're going to solve some problems using this expression and find out what is the attenuation for different length of the optical fibers and also for different parameters like input power and output power. So the standard unit, again, in the industry standard unit for representing the loss is dB milli, dBm, and you can see how to convert dB milli, how to convert loss in dB to dBm. So loss in dBm is equal to 10 log to the base 10 of uh, loss in watts divided by 1 milliwatt. So you can see this expression loss in decibels milli is equal to 10 log to the base 10 of loss in watts divided by 1 milliwatt, which will give you the value in terms of dB milli. So once you solve the problems, you will have a better understanding of how to convert dB to dB milli. So this is an example problem which is considered here. I'll just read out the example. The optical powers are expressed in dB milli, and the power level is referred as 1 milliwatt. Consider the length of the fiber as 30 kilometer and attenuation of 0.4 dB per kilometer at the wavelength of 1310 nanometer. If the output power is 200 microwatts launched into the fiber, output power is 200 microwatts, and we are supposed to estimate what is the power in dB milli, output power in dB milli as well as input power in dB milli. So input power is in dB milli 10 log to the base 10 of power in watts divided by 1 milliwatt. I think this should be P in. Input power is 200 microwatt. Okay. So 10 log to the base 10 of input power in 200 microwatt divided by 1 milliwatt will give you power in dB milli. So using the same expression for output power, P output power in dB milli is 10 log to the base 10 of P output power in watts divided by 1 milliwatt. As we have already used this alpha, which is nothing but the loss, and the loss is mentioned in terms of dB per kilometer. In the question, they have mentioned as 0.4 dB per kilometer. So it is 10 log to the best of input power in dB milli minus the loss, which will give you the output power. So input power in dB milli is minus 7 dBm, which is estimated minus 7 dBm minus of alpha is 10.4 into 0.4 dB per kilometer, and the length of the fiber is uh, 30 kilometer. So 0.4 dB per kilometer into 30 kilometer will give you uh, minus 19 dBm. This is the output optical power, that is in terms of dB milli. So if you want to convert back that into watts, you just have to take the antilog of that and multiply with 1 milliwatt. That will give you the output optical power of 12.6 microwatt for an input power of 200 microwatts. So you're getting an output optical power of 12.6 microwatt after it has propagated a distance of 30 kilometers. So you just can understand the attenuation which is being caused in optical fiber as it has propagated a length of 30 kilometer. So 20 microwatt was the input power, which got converted into 12.6 at the output after it has traveled 30 kilometer distance.
Sir, can you
Second
send the
problem where
PPT and the document, sir?
hello,
Hello, sir, can you send this PPT and the document?
yeah,
Okay, sir, because it will be easier for us to see the problem.
what do you want?
I want on the Google Classroom, can you send the same, sir? Maybe after the session, not a
Yeah,
problem.
I'll just forward it later. Later
Thank
I'll
you, sir.
forward it. Yeah. So this is the second problem which discusses about the overall signal attenuation. Determine the overall signal attenuation in dB throughout the fiber. Assuming there are no connectors or splices, please understand this problem. We have an optical fiber system which is established, and it cannot be established just by using an optical fiber for the entire length. In between, we are supposed to connect connectors or splices. So if we, in that case, we need to cut down the optical fiber and place the connector and re-establish the connection. So this is a problem which tells us uh, uh, if there are connectors, the loss will increase. So to what extent the attenuation or the loss will increase if you are placing the connectors or splices. So second is signal attenuation per kilometer for the fiber and overall signal attenuation for 10 kilometer length optical fiber link, in which for every 1 kilometer there is a fiber splicing which is being done for every 1 kilometer, and each splicing will introduce an attenuation of 1 dB. So signal attenuation, that's the first thing which is asked in this problem. So the expression is 10 log to the Weston of P naught by Pi, or it is minus 10 log to the Weston of P naught by Pi, or 10 log to the Weston of Pi by P naught, which will give us 16 dB. You just have to calculate, use the value of the previous problem, and you can just apply the P naught and Pn, and you will be getting the signal attenuation. And for every 1 kilometer, if the fiber length is 8 kilometers, so total attenuation divided by total length of the fiber will give you 2 dB per kilometer for every 1 kilometer. This is the attenuation loss. And if it is 10 kilometer, if the fiber length has been extended from 8 kilometer to 10 kilometer, as we already know that per kilometer attenuation loss is 2 dB per kilometer, one can easily calculate for 10 kilometer, that is 2 into 10, which will give you 20 dB. If the fiber length is changed from 10 to 30, it will be 2 into 30, that will give you 60 dB. So coming to the third part of the problem, if there are 9 splices, if there are splices which are placed for every 1 kilometer, if you take a 10 kilometer length of the fiber, we need to place 9 splices. That means to say from one starting point to 1 kilometer, one splice, and till the end we need to place splices for every 1 kilometer. So totally 9 splices can be placed for a 10 kilometer link, optical link. And each splice is going to introduce a loss of 1 dB means. So with 9 splices into 1 dB will give you 9 dB as a attenuation loss due to splicing. So loss because of the fiber is already 20 dB, and loss because of this splicing 9 splices it is 9 dB. Overall signal attenuation will give you 20 plus 9, that is 29 dB. So that's the overall attenuation loss after you have placed the splicing for every 1 kilometer. So I'll stop the session at this point. The second module we just have to go through the problems of attenuation. Whatever I've discussed today, we have discussed two problems. One is converting power in terms of watt, dB milli, and also in terms of watts, and calculating the attenuation loss, overall attenuation loss, and attenuation loss per kilometer. And what if you are going to place a connectors or splice in between, so how the attenuation will increase. So in second module, attenuation and bandwidth, these are the two important things which we will be understanding throughout the module. So first part of this second module was attenuation, and the introduction to attenuation is in terms of overall loss, and types of attenuation will be discussed in the next lecture. So I'll stop at this point. If you have any questions, you can ask for 2 minutes so that we can end the session here. Hello. Okay, fine. I'll be ending the session now. Thank you all for attending the session.